Hey everyone, welcome to another lecture in the calculus series by the ML Hub. So in today's lecture, we'll be diving into the world of inverse functions. So it's a very powerful concept that helps us reversing the effect of a function. So if a function takes us from input to output, the inverse bring us back to the input. So let's see how this works. So what is the inverse of a function? As I said earlier, an inverse function reverses the operation done by a particular function. So when we studied functions, so it's a functionality that is triggered from input to output. Okay, so inverse is basically undoing that functionality or making the functionality in reverse direction from output to input. A very popular example when it comes to compressing a folder which is having a zipping operation. So suppose we have a folder, we perform a zip operation in order to have a lossless compression on a set of files. So we get a zipped file. A zipped file which is less in size, which is compared to the original file. And then so that it enables us to transfer it in a very convenient manner as well as without losing any information. So reverse functionality can be thought of as unzipping that file in order to get the original file, so that we end up from where we started. So if it is x, we applied a zip operation to get y, and then we applied unzip operation again to get x. So this x and this x is equal or similar. So this is what inverse function does. Okay, so a function and its reverse operation. So if y is equal to fx, it's a transition from x to y. So inverse is denoted by x is equal to f inverse of y. So this is how the inverse of function is denoted. This is an operation from y to x, basically a undid operation. But you have to be very careful when it comes to inverse of an operation. Not all operations or not all functions are revertible or reversible. Okay, so we'll be discussing which functions are reversible, which are not, and later in this lecture. But for now, inverse of a function is basically a reverse operation. That's it. So let's see the formal definition of an inverse. So given a function f with domain D. So f is a function defined from domain D to a range R. The domain is D and the range is R. So its inverse function, read it carefully, if it exists. So as I said earlier, not all functions are invertible. So the inverse function, if exists, is the function denoted by f to the power minus 1, and it is read as f inverse with domain as R. So the new domain of the inverse function will be the range of the original function, and range is D. So if a function is defined from D to R, then its inverse, if that exists, will be a function from R to D. So this R is the new domain. New domain of f inverse, which is equivalent to the range of f. Similarly, this D is the new range, is the range of f inverse, which was initially the domain of f, such that f inverse y is equal to x if fx is y. So again, a very important operation. What it says, if y is equal to f of x, then f inverse y will be x. Okay, and f inverse of f inverse x is again x. And when you try to have an inverse operation on the original function, so what it will give? It will give you the input, which is x. Applying inverse on the original function, which is y, will give you x for all x in the domain. and f of f inverse y. If you apply the original function on the inverse, it will give you y for all y's in R. Okay, why? What it means? It means basically you have a function you applied on x to y. Now you applied the inverse function from y to x, you will get the original x. That's it. So this is x, which is domain of f, and it is also the range of f inverse if inverse exists, and the same time the range of initial function f, which is y, will be the domain of f inverse, and they are inverted. Basically we can have a transition from x to y through f, x to y through f, and from y to x through f inverse. Okay. So now the question arises, does every function have an inverse? So given a function, how can you say or how can you identify whether there exists the inverse of this function or not? So for that, we need to, if you remember what exactly the definition of a function is. So a relationship between two set A and set B. That relationship will be a function if and only if every input is mapped with exactly one output. Okay. So if I am saying that f inverse is a function, then this definition also holds on f inverse. So f inverse will only be existing in nature if each input is mapped with exactly one output. And I am talking about f inverse, not f. We already know that f is a function. It is given to us. We are checking whether f inverse exists or not. So for existence of f inverse, each input of f inverse should be mapped with exactly one output of f inverse. So let's see what exactly this statement means. So if you remember, there are like 4 types of relationship that exist between two sets, or you can also call them mapping. The first one is one-to-one mapping, which is every input is mapped with exactly one output. The second one is one-to-many mapping, in which one element of set A is mapped with multiple elements of set B. For the instance, which is the first case, one-to-one mapping, you can have this example, fx is x plus 2. What it says, if you have two sets like this, each element is mapped with exactly one element like this, and so on. Okay. So what it says is each input is mapped to a unique output. No two inputs share the same output. So if this holds, the mapping is known as one-to-one mapping. And can we call it a function? The answer is yes, we can. This is a function. This will be, if this mapping exists, it will be a valid function. The second one is one-to-many, which says a single input maps to multiple outputs. Okay, for example, a person has multiple phone numbers. So one input resulting into multiple outputs. So this will be the case. Given two sets, one input is mapped with, say, two outputs like this. So is this a function? The answer is no, it is not a function. The third one will be many-to-one. There can be a many-to-one mapping, right, which says multiple inputs map to the same output. But this mapping exists, and this mapping is also a function. Why? Because it is satisfying the definition. For each input, you are getting a unique output. It says many to one, multiple inputs. For instance, it will be like this. Multiple instances are mapped with the same output. For example, this function y is equal to x square. It is like this. So at any y, you are getting 2x, this and this. So it is a valid function. The fourth one is many-to-many mapping, which says multiple inputs mapped with multiple outputs. So again, obviously it is not a function. Why? Because for one mapping in the domain, for each element in the domain, we are not getting a unique or exactly one output from the range. You can have an example, people and their favorite food. Multiple people can have multiple foods as their favorite. Okay, so out of these four mappings, only two are functions, which is one-to-one and many-to-one. Why? Because these two are satisfying the definition. Each input is exactly mapped with only one output. But out of these two, only the first one, which is one-to-one, will be satisfying this definition of F inverse. Why? Because we already seen if F is defined as a function from D to R, then F inverse will be a function from R to D. So if the function is many to one, then F inverse will be one to many. If F is many to one, then definitely F inverse will be one to many. And if a function, let's assume we call F inverse as G, a new function where domain is R and range is D. Same configuration. It will be a one to many mapping. And if this mapping is there, in that case it is not a function. It is not a function. So only the functions which has one-to-one mapping are invertible. Clear? So for instance, you can have an inverse of this function y is equal to x square, but you can't have an inverse of this function y is equal to x square. Understood? Okay. So one-to-one functions. So let's have like one more test, same as what we saw when we were defining the function. At that time we studied about the vertical line test, but here to find whether the function is invertible or not, we will be having a horizontal line test. What it says, a function f is one-to-one if and only if every horizontal line intersects the graph of f no more than once. So if this holds, in that case it is invertible. So it is another way of saying that it should be a one-to-one mapping. If it is a many-to-one mapping, in that case you can't invert. So any curve, any graph you can consider with a many-to-one mapping, so it won't pass the horizontal line test. Why? Because multiple inputs are mapped with the same output. So the invertible function will be a one-to-many mapping in that case. For instance, you can take a example of a parabola. So this is many to one. Why? Because of this case, a y is mapped with two x's. Same for here. You draw any horizontal line, it will intersect the graph at more than one points. So if it is intersecting at more than one point, so it is not invertible. That's why this is a non-invertible function. But at the same time, if you consider the graph of y is equal to x cube, you draw any horizontal line, it will intersect the graph exactly at one place. So this function passes the horizontal line test. Therefore, it is a invertible function. So all one-to-one functions are invertible. And only one-to-one functions are invertible. Many-to-one functions are non-invertible. So therefore, they will also pass the horizontal line test. Okay. So let's have an example. Given three different functions three different graphs. Which one is a invertible function, which is not? So let's see. In the first one, it is already defined. So 1, 2, 3, 4, and so on. So yeah, if you have a horizontal line anywhere, it will always give you only one value. Why? Because this is not inclusive. This is not inclusive. So for this line is y is 1, x is 0. Not 0, x is 1, not 2. Why? Because it is 2 is not including in this. Similarly, for this 1, 2, 3, 4, y is 4. So x will be 4. So this is invertible or 1 to 1. In this case, y is 1 by x. Try to have a horizontal line anywhere in the domain. You will always get a single value. So this is also 1 to 1. Now let's see the third one, x cubed minus x. So if you draw a line, horizontal line here, you are getting only 1 point. But as long as the y is from 0 to 2, y is from 0 to 2, you are getting 3 intersecting points, which is more than 1. If for any y you see this sort of instance, straight away you can say it is not 1 to 1. So it's a non-invertible function. Alright. So now what are the steps? How can we find the inverse of a 1 to 1 function? Say let's assume the function is given to us, or we have identified that this corresponding function is a 1 to 1 function. So now how can we find the inverse of that function? Let's see that. So simple 3-step process. Step 1 is to solve for x. What it says? Given this equation y equals f of x, you start from this equation and solve for x. You try to have multiple sort of operations on this equation in such a way that the resulting equation is in this form: x is equal to some function of y. Okay, this is the first step. The second step, then interchange x and y. So after you have this equation, which will be of the form x is equal to f of y, you interchange x and y to have new equation. The equation remains the same. We are just interchanging y from x. It will give you y is equal to f of x, and this is what f inverse of the original function is, which is the third step. Write the inverse function as this: y is equal to f inverse of x. This is y is equal to f inverse of x. So let's see an example. So if f of x is given to you as 3x minus 4, if f of x is 3x minus 4, what is the step 1? Solve for x. I can write f of x as y. So if I want to solve it for x, it will give me 3x is equal to y plus 4. So this gives us x is equal to y plus 4 by 3. The first step is over. The second is interchange x and y. Change y from x. This will give me y is equal to x plus 4 by 3. What I did, I just interchanged y and x. That's it. The third step is write the inverse function as y is equal to f inverse of x. This is what the inverse is, which is y is f inverse x, which is the function is x plus 4 by 3. So this is the inverse of the original function, which is 3x minus 4. Okay. So similarly, you can also solve for y is equal to x square minus 2x. X square plus 2x for x greater than equal to minus 1. What do we have? We have fx is equal to x square plus 2x for x greater than or equal to 1. So let's see the second example. How we'll be calculating the inverse of this function. So again, it will be the same 3-step process, starting from the first step, which is we need to solve it for x. So it's x square plus 2x. So it is a quadratic equation. You can have the perfect squares. This will give us y plus 1 will be x plus 1 whole square. So therefore x plus 1 will be plus minus square root of y plus 1. Therefore x will be plus minus y plus 1 minus 1. But since it's given that domain is x greater than 1, so we will be discarding this negative and it will be only positive. Why? Because x less than 0 is not in the domain of the original function. So then the second step, this is step 1. The second step is to convert x and y, you interchange x and y. So it will give us y is equal to x plus 1 minus 1. So this is what f inverse x is. And what will be the domain? The domain will be equal to the range of the original function. So to find the domain of the inverse, we need to find the range of this, since x is greater than 1. So if x is 1, then f of x will be 1 plus 2, which is 3. And later when we study about continuity, we will be seeing that this is a continuous increasing function. So for any x greater than 1, this will always, f of x is always greater than 3. So the range of this function, the range is three to infinite. So this will be the domain of f inverse, which is 3 to plus infinity. Okay, and the range will be this, the domain, which is y greater than or equal to 1. Or you can have it like this, the range will be like this. All right. So now, if a function is given to you, a function y is fx is given to you, and you have been asked to draw the graph of f inverse x. So let's see how we can draw the graph of a inverse function. So if a point a comma b is given, a point capital A, coordinates are small a comma small b, is given to us, which is lying on the graph of the function f. So we have a function, can be anything. Let's assume this is the function, and there is a point. There is a point capital A which lies on f, Then the point b comma a will be on the graph of f inverse. So if we find f inverse and try to draw the graph of f inverse, then the point with inverted coordinates, x will become y will become x. So the new coordinate will be b comma a. This will always be present on the graph of f inverse x. What it means? This means the graph of f inverse reflects the graph of f across the line y is equal to x. So if we try to have a line, this is y is equal to x. So the graph of f inverse will be the reflection of f, which is this y, on this line, which is y is equal to x. Why? Because we are saying that f is a one-to-one function and inverse exists. So a comma b will become b comma a. So we just need to reverse the values of a comma b with respect to this line y is equal to x in order to draw the graph of f inverse. That's it. Okay. So visually f and f inverse are the mirror images. F and f inverse are the mirror images over the line y equal to x. So you do not have to do anything. Just find what is the graph looks like of f, and if you know that it is a one-to-one function, you can have it a horizontal line test to verify this, or you can also find any specific y for which you are whether you are getting two different x's. If no, in that case it is one-to-one, then just have the mirror image in the line y is equal to x of f in order to find the graph of f inverse. That's it. So let's see an example. Given two graphs A and B, how can we find the graph of y is equal to of f inverse x? We need to find the graph of f inverse in both the cases. So simply, let me draw the line y is equal to x. So this is y is equal to x. Same I will do it with this. And the next step will be to find the mirror image of this fx, which is y, into this line. So the mirror image will something look like this. This will always pass through this. Why? Because it is intersecting, the y is equal to x is intersecting f of x. So the mirror image will be something like this. It is not perfect, but yeah, this is y is equal to f inverse x. So this a comma b will be present here as b comma a. Okay. So similarly, in this case as well, you can find the mirror image. It will intersect here. It will look something like this. Okay. This is y is f inverse x. And again, you can have any point. This point is here. If it is a comma b, this will be b comma a. Okay. So that's all. Like, you can have mirror image of any graph in the line y is x. Now let's discuss the next topic, which is restricting domains. So as you can see that we have certain functions which are not one-to-one. So there are two sorts of like relationships or mapping which leads to a function. The first is one-to-one, the second is many-to-one. Both the cases it is a function, but if the function is one-to-one, in that case it is invertible, inverse exists. If it is many-to-one, in that case it is a function, but inverse is not a function. So inverse doesn't exist. So here comes the restricting domain. In order to make a many-to-one function, we have a function which is many-to-one. Can we restrict the domain, or can we restrict the possible values of x in such a way that f becomes one-to-one from many-to-one in order to find the inverse of that function? This is what restricting domain is. So let's see this with an example. So we have a function y is equal to x square. and we already know it is a many to one function. So inverse doesn't exist. But what if this is 0, comma 0 origin? So there are two intervals. The first interval is this. Let's call it I1. The second interval is this. Let's call it I2. This is I1 and this is I2. I1 is from 0 to plus infinity and I1 is minus infinity to 0. So if I restrict the domain of x and like original function f, the domain is minus infinity to infinity. Okay, all values of x are possible. So if I am talking about this domain, then the function is not invertible. It is many to one function. But what if I restrict the domain only to I1? If this becomes the new domain, if this becomes the new domain of fx is equal to x square, can I say that the function becomes one to one in this new domain? Yes or no? What it means is I am restricting the value of x like this. The new graph will look like this. Y is equal to x square for x greater than equal to 0. It is passing the horizontal line test, right? Now it becomes a one-to-one function. Now it becomes a one-to-one function. For each value of y, you are only getting exactly one value of x. And this is what restricting domain means. If y is x square, which is not a one-to-one function, so it has no inverse. Inverse doesn't exist if you are taking the entire domain for x over all real numbers. But what if I restrict some values of x from the domain in such a way that the new function becomes one-to-one? The new function becomes one-to-one. In that case, I can say that after restricting the domain, the many like you can have multiple many to one function will get converted to a one to one function and will be invertible. So this is what it says. So this is invertible if the domain is this I1. It is also invertible when the domain is I2. The same time, this will be the case. Function will look like this. This is again y is equal to x square when x is less than equal to 0. Okay. So it is interesting to have these restricting domains and try to find how the graph of the function, which is f inverse x, will look like if I am restricting the domain to all positive numbers. The second case, I am restricting the domain to all negative numbers. So let's see that. Case 1, which is y is equal to x square, where x is greater than equal to 0. And case 2, y is x square when x is less than equal to 0. Both the cases, case 1 and case 2, are invertible. So when it comes to case 1, this is the function. Okay, and when it comes to case 2, this will be the function. This is your x-axis and this is your y-axis. And the line, what I'm trying to do, I'm trying to find how will be the function, the graphical representation of f inverse in both these cases. So here is the line, y is equal to x, This is the line, y is x. This is case 1. This is case 2. So if you want to have the graphical representation of inverse, you need to have the mirror image of this graph into this line, y is x. So it will be not like this. It will be like this. This is y is f inverse x. And same in this case, it will be like this. Okay. So this is how the graph of inverse will look like when it comes to case 1 and case 2 after restricting the domains. All right. It will be like this. And when it comes to the second case, if we try to have a reflection of y is equal to x square over here, it will look like this. This is y is f inverse x. And in fact, it will be under root x, and it will be minus under root x. Okay. All right. So let's see a problem which says which of the following is the graph of this equation. The equation is given to you. Square root of mod of y is equal to x, and 4 options are given. You can pause here and try to find what will be the correct option. So let's see the solution. So we'll be starting from the equation which is given to us. What it says square root of modulus of y is x. So what it says is x can't be negative. The information that I can infer from this equation is x can't be negative. Why? Because square root cannot give you a negative number. Therefore, x will be greater than equal to 0. The first thing. So if x is greater than 0, then option A eliminates. Why? Because the graph is defined for negative x as well. Now, modulus of y is equal to x square. So the next step will be to remove this modulus. So to remove this modulus, I need to define this function in a piecewise manner. What it is? It will be x square if y is greater than equal to 0. It will be minus x square if y is less than 0. This will be the piecewise definition of this function if I am removing this modulus. Okay, why? Because it can't be negative. So for positive y's, the function will become x square. For negative y's, the function becomes minus x square. So if y is equal to x square, the graph of y is equal to x square is like this. And the graph of y is equal to minus x square is like this. So what I need to do is, if y is positive, which is this case, if y is positive, I need to take this into consideration. If y is negative, I need to take this into consideration. So B will be the right answer. Okay. So now let's discuss about inverse trigonometric functions. So when it comes to trigonometric functions, we have already studied that all these trigonometric functions are periodic in nature. So if a function is periodic, f of x plus p, where p is the period, will be equal to f of x. So they are not one-to-one functions. They are many-to-one functions. And you can also see from the first example, this is the graph of sine x. If you try to have a horizontal line in the domain, if you try to have a horizontal line in the range, not domain, it will intersect the graph at multiple points at one intersection in each period. So you will get multiple intersecting points. So it fails the horizontal line test. Trigonometric functions will fail or are not one to one or are many to one functions. But at the same time, we have also studied about restricting the domains. So what if I restrict the domain of these trigonometric functions in such a way that in that domain there is no more than one intersection of that horizontal line? In that case, it will become a one-to-one function. It will become a one-to-one function if I restrict the domain. How? So let's assume the domain as minus pi by 2 to pi by 2. If I only consider this domain minus pi by 2 to pi by 2, can I say that this function, after restricting the domain, this becomes a one-to-one, and as soon as the function becomes one-to-one, inverse is possible. And similarly for y is cos of x, if I restrict the domain from 0 to pi, this function becomes from 0 to pi, this will be a one-to-one function or invertible. So like, as you can also see, if I just cross this, let me explain. If I just cross this domain from pi by 2, I am writing the parabola in downward direction. Any horizontal line is intersecting at 2 points. So therefore, even after I increase the domain from pi by 2, it won't be a one-to-one function. So exactly in this domain, which is minus pi by 2 to pi by 2, sin x is invertible, and 0 to pi, cos x is invertible. And like you can also argue that it is also invertible in this domain, which is pi to 2 pi and so on. The answer is yes, it is, but for convenience, we usually take the first interval, which is 0 to pi for cos and minus pi by 2 to pi by 2 for sine. Alright, so these are the graphs, and as I mentioned earlier, you can all easily have the graphical representation. How? Just see the graph of sin x, try to have the mirror image in this domain from minus pi by 2 to pi, try to have the mirror image in the line y is equal to x in order to find what will be the graph of these inverse functions, inverse trigonometric function. And this is how they are, like the inverse is denoted sine inverse of x. It is read as sine inverse x, and some, like many places, you can also find it as arc sine x. Both are equivalent. Okay, and this is also read as sine inverse x. So this will be the graphical representation of sin x, this will be the graphical representation of cos inverse x, and this is how the tan inverse x graph looks like. And in the previous slide, we have seen that the domain of sin x, in order to make it a one-to-one function, was minus pi by 2 to pi by 2, and the range was minus 1 to 1. Again, the domain here for cos would be 0 to pi, and the range is minus 1 to 1. So if I need to find the inverse, the domain will be the range of original function, which is the non-invertible one, which is sin x. The new domain will be the range of sin x. The range of sin x is minus 1 to 1. And the range of inverse will be the domain of sin x, and that would be minus pi by 2 to pi by 2. Similarly for cos, the domain will be minus 1 to 1, and the range will be 0 to pi. And for 10 also you can have the domain is all real numbers and the range is minus pi by 2 to, this is the range, minus pi by 2 to pi by 2. Alright, similarly you can also have the inverse graphical representation of cot, cosec and sec. So here is the consolidated table having all the inverse trigonometric functions along with their domain and range. Okay, so to ensure that the trigonometric function remain one to one, this will be the range, this is the range of the inverse, so this will be the domain of original function. Alright, so the range now becomes, the domain will be, as we discussed, minus 1 to 1, range will be minus pi by 2 to pi by 2. For cos inverse x, the range will be minus 1 to 1 and the domain will be minus 1 to 1 and the range will be 0 to pi. For 10, it will be all real numbers and it is minus pi by 2 to pi by 2 and it is open, not closed. For why? Because at pi by 2 and minus pi by 2, we are going towards infinite. So the tan inverse x is not defined. And similarly, you can have for cosecant, secant and cotangent. Okay, so all the angles which are not part of this range, so the value is undefined for all these points. That's why it is removed from the range and the domain of corresponding inverse functions, inverse trigonometric functions. So let's have one more example. Given a function tan inverse x plus 1 by 2 sine inverse x, what will be the range of this function? Alright. So let's see. The function is given to us as fx is equal to tan inverse x plus 1 by 2 sine inverse x. So in order to find the range of this function, first we need to find what will be the domain of this function. And I am once again asking you guys to keep this in mind. Keep the domain and the range both for inverse as well as the original trigonometric functions in your mind in order to smoothly solving these sort of problems. So this problem involves two inverse functions, tan inverse and sine inverse. So in order to find the domain, we need to know what is the domain of both of them. For sine it is minus 1 to 1, but for tan inverse it is all real numbers. So apart from minus 1 to 1, this function will be undefined. This function will be undefined. Why? Because sine is only defined from minus 1 to 1, but tan is defined from minus infinite to infinite. So if I need to have the addition, if I am talking about this function, the domain will be the intersection of these two domains. The domain will be minus 1 to 1. Got it? Why? Because any x which is not part of this domain, minus 1 to 1, this sine inverse x would be undefined. So now if we have the domain, we can easily find the range. We just have to find the values of fx at these points, minus 1 and 1. And later in the course, when we discuss about continuity, we will see that it is an increasing function. That's why we can directly calculate the range from the domain, which is minus 1 to 1. For now, you can have this assumption that we are finding the values of fx at minus 1 and 1, and then we'll see, compare it with the option in order to find the correct one. So f minus 1 will be tan inverse minus 1 plus 1 by 2 sine inverse minus 1, and tan inverse minus 1 is minus pi by 4 plus 1 by 2 sine inverse minus 1 will be minus pi by 2. So it is minus pi by 4 which is minus pi by 2. Similarly, we can find the value f of 1. It will be tan inverse 1 plus 1 by 2 sine inverse 1, and it is pi by 4 plus 1 by 2 pi by 2. So again it is pi by 4 plus pi by 4. So f of 1 is pi by 2. So let's see the options. So it is not including pi by minus pi by 2 and pi by 2. So it's incorrect. B is also incorrect. C seems to be correct. And D minus pi by 2 is not included in this. So D is incorrect. So the right answer is minus pi by 2 to pi by 2. So there can be some instances in which even after finding the domain, you might come across certain points for which the function is not defined. In that case, you need to take that into consideration. So though these things will only happen for non-continuous or non-increasing sort of functions, non-increasing or non-decreasing. But in this case, like, you can have an assumption that it is increasing in nature, and we will discuss this briefly and whenever we will be discussing about continuity. So for now, C will be the right answer. Okay, so that's all for this lecture. These are the references that I'm using to prepare these lectures. And again, hope you guys enjoyed this session. See you in the next class.